Okay, so this is 1.2c, rationalizing denominators or instructional objective. I will be able to rationalize denominators and practice choosing the most efficient factors. That is a skill that you have to work on and build, choosing the most efficient numbers that are going to help you rationalize the denominator. Okay, so that is our instructional objective. Your notes there are your important definition. It says what's rationalizing a denominator. So see that on your notes. It's rewriting the denominator as a rational number by multiplying a fraction times 1. Which probably doesn't make a lot of sense, but once we put it into practice, it will. So that's what rationalizing a denominator is. Rewriting the denominator as a rational number by multiplying a fraction times 1. So what does that look like? So I'll put it in a more basic fraction form. Is this a true statement? If I multiply 2/3 times 5/5, that's times 1, right? Because times 5/5 equals 1, right? It gives me an answer of 10/15, but is 10/15 equivalent to 2/3? Yes, it is, right? So what I did was I rewrote 2/3 as 10/15 by multiplying it times 1, and I got 2 equivalent fractions. So that's what we're going to be practicing here. The difference is our denominators are going to be irrational, and we're going to have to make them rational. So all of the knowledge that you have is going to help you make the determination which number are you going to use to take this irrational number and make it a rational number. Okay, so let's first start with, let me clean that up, your division property of radicals, which is really useful. And it says on your paper, the nth root of a over b is equivalent to the nth root of a over the nth root of b. Now, we learned that last week, but we're still using it. It's pretty powerful once you master it to know that sometimes it's better to put two numbers under the same root because you can simplify things and be efficient, and sometimes it's better to take them apart so that you can be efficient and simplify. So let's say we have the square root of 5/3, which I gave you. And we're going to talk about if that's very efficient. Okay, right now my denominator is a square root of 3. And can I simplify 5/3? Can I simplify it into a nice even whole number? 5/3. 5 is not divisible evenly by 3. Okay, so if this denominator is totally irrational, I'm going to separate them and say that it's the square root of 5 over the square root of 3. In this situation, if I'm going to rationalize that denominator, the square root of 3, I have to separate it from the square root of 5. I couldn't simplify it, so it was just better to pull them apart. Let's do another one next to that. What if I had the square root of 10 over the square root of 5? So I have them separate. Would it be more efficient to leave them separated and rationalize my denominator, or put them under the same root? Same root, right? It is way more efficient to put them together because 10/5 is the square root of 10/5 is the square root of 2. And the denominator's of 1. It's over 1. It's a rational denominator. So we have to learn as we're going through these, and you're not going to get a full mess of practice with it right now, but you're going to start learning when to make that decision. Do I keep them together? Do I take them apart? What do I do? All right, so let's go look at A, and let's talk about how do I rationalize its denominator? Excuse me. How do I take the number 1 and divide it by this non-terminating, non-repeating decimal that goes forever and ever and ever? It's not possible. So what do I do to make that square root of 7 become a whole number, a beautiful rational number? I'm wanting to multiply this fraction times 1, because if I multiply it times 1, it still has the same value. It's equivalent. Well, what can I do to get that square root of 7? That's 7. How can I get it out of the square root? What can I multiply it by? So think about this. This is 7 to the first power. Do you see something, Seth? But the reciprocal would be creating a 1 every time. When you multiply a fraction times its reciprocal, you always get 1. What I'm wanting to do is multiply times 1, so it still equals the same thing. So this is 7 to the first power. Do you agree? Now, how do I get a square root to disappear? What's its opposite of a square root? A square. So could I multiply this times the square root of 7? Because what's that? What's the square root of 7 times the square root of 7? It's 7, because it's the square root of 49, which is 7. But if I'm multiplying the denominator by the square root of 7, I have to multiply the numerator by the square root of 7, because I have to multiply it times 1. If I want the final answer to be equivalent. So I'm going to multiply those together, and I get the square root of 7. I'm not going to skip steps. I'm going to call that the square root of 7 squared. You don't have to write that down if you get it. That's fine. Perfectly fine. I'm just following my rules, which gives me the square root of 7 over 7, because squares and square roots cancel each other out. They're inverse operations. Okay, so in that situation, the number I chose was the square root of 7. I didn't choose a bigger number, and I certainly didn't pick like the square root of 2, because 7 times 2 is 14. The square root of 14 is not perfect either. Okay, so let's see if you get it. Let's try B. For B, you have the cubed root of 2 over the cubed root of 7. Now, the cubed root of 7 is irrational. It's not a perfect cube, non-terminating, non-repeating. Thinking about that, I can only multiply it by 1 and keep it equivalent. But what form of 1 am I going to multiply it by? What do you think? 7 cubed? If I go by 7 cubed, that'll make 7 to the 4th. You're on a good track. Do I need 3 7s? Or just 2 more? How do I make this equal the cubed root of 7 cubed? What do I need? Cubed root of 7 squared times the cubed root of 7 squared. Okay, that'll get me to the cubed root of 7 cubed. Right? Okay, in my numerator, I'm actually going to have to do some math here. I'm not going to get any nice little canceling of cubes and cube roots. I'm going to have to multiply 2 times 49, which is 98. So I'm going to just write a little 49 over that 7 squared, because I actually do have to multiply those and use the product property. And then in the instructions, it says to be careful to simplify my final answer. So I'm wondering if, I got to finish, I can simplify the cubed root of 98. What do you think? Because I always have to be careful to check. Anytime I write an answer in fraction form, I need to know, is that in simplest form? Are there any perfect cubes in 98? Logic. 98 is what? We just did some math right here. 2 times 49, and 49 is, and that's prime. Do I have a cube there? I got a 2 to the first and a 7 squared, and none of those are cubes. So it cannot be simplified. That's all it is. The cubed root of 93 over 7. But the denominator is rational now. Okay, questions? Okay, let's try the next one, letter C, which is the cubed root of 3/4. So now a little bit different. We have both the numerator and denominator under the same cubed root. And my question is, can I simplify them in this form or should I separate them? Can I simplify 3/4 into an even number? No. Okay, so I'm going to separate them. And now, remember how I told you that you're going to have to learn to be efficient? Cubed root of 4. So we're going to get rid of that root in the denominator. Now I'm going to pick a number, and it's probably not the number that you're thinking of. What are you thinking? I should multiply this by so that I have a rational number in the denominator. I'm thinking times the cubed root of 2. Now you might have been thinking the cubed root of 4 squared, right? Because you're trying to get to 4 to the 3rd power, right? Maybe that's what you were thinking of. I'm thinking the cubed root of 2 because I see 4 as 2 squared. And that's one that I can pretty easily do in my mind. And I do this because it's more efficient. If I use 4 squared, I'm going to have a big fraction at the end that I have to simplify because my numbers are going to be greater. So I'm multiplying everything times 16 instead of everything times 2. So I would say that it would be better to do the cubed root of 2 over the cubed root of 2. Now the reason for that is that I'll get the cubed root of 6, right? Because you use your product property, put them together, over the cubed root of 8, which is a perfect cube. Cubed root of 8 is 2. And so my final answer, I'm pretty sure, is the cubed root of 6 over 2. Because I'm pretty sure there's not a perfect cube in 6. 2 times 3, right? So why is it that that was more efficient? Let me show you what happens if I was going along, cruising along, thinking, yeah, I got this. I don't have to pay attention anymore. Okay? If I did this, cubed root of 4 times the cubed root of 4 squared, this isn't wrong. It's not wrong. It's just not super efficient. So that's 16. You agree? Just watch. Yes, you agree? So this is the cubed root of 48 over the cubed root of 4 cubed, which is 4. So I'm skipping steps a little bit here. But I can tell you that those two answers that we got are not the same. I mean, they're equivalent, but they're not the same because there's a perfect cube in 48. There it is. You know what it is? 8. Yes? Isn't 48? Could I say this is the cubed root of 8 times the cubed root of 6? Yes? Over 4. And what's the cubed root of 8? 2. So I would have 2 cubed root of 6 over 4. And you know what I have to do with that? Simplify it more. And so you can see that it starts to create the situation where the problem takes longer to solve. You can either think at the front or work at the back. Do you know what I mean? Take some time to think. What's my best choice? Or work at the back to simplify. They both work. They both get you the same place. Okay, so it looks like the bell's going to ring. Yes? Here's what I'm changing the homework. Make corrections if you have it. That's it. You don't have anything.
What are we doing?
Okay, those of you that are watching the video, you have homework.